Good afternoon all. Last class we studied about switching off transistor. Switching off operations, we have seen cutoff region as well as saturation region. Cutoff region, when there is no input, your transistor will be in off condition and works as a switch. It's in off condition. Same way, when input is given to VBB, that is nothing but your base of a transistor. Your transistor will be in saturation region. It's nothing but it is on. And it is nothing but a closed switch. That's what we studied in the last class. Now we will see how a condition in cutoff region, saturation region performs by the transistor. See, when in the cutoff region, when the base to emitter junction is not forward biased, then there is a negligible leakage of current. All the currents are 0. So VC is equal to VCC. So if you observe here, collector to emitter will be equal to VCC. That's what we are given. VCE cutoff is equal to VCC. Coming to saturation region, when the base to emitter junction is forward biased and there is enough base current to produce a maximum collector current, the transistor is in saturation region. That means the transistor is in switched on. To see this, there is a formula for a collector saturation current. That is nothing but IC saturation equal to VCC minus VCE, collector to emitter saturation, divided by the current flowing through the collector, that is through RC. Since VCE is very small compared to VCC, it is usually neglected. You can see here IB, that is nothing but the current flowing through your base of the transistor, is given by IC divided by beta DC. So always you have to see IB should be always greater than your IB minimum. Significantly it should be greater for the transistor to be in a normal condition, or you can call it as saturation region or active region. As we can see here, figure 4.24 is nothing but the circuit we have shown here. It has an input voltage of 0, and we have a problem here. What minimum voltage of IB is required to saturate the transistor? That's nothing but your transistor to be in on condition. So they are given some beta value here. Beta DC is 200. So here we are neglecting VCE, that is nothing but collector to emitter voltage for a saturation of a transistor. Then we are going to calculate the maximum value of RB when the input voltage is 5 volts. So let us solve this. When Vin is equal to 0 volts, so there is no input to this. So when there is no input to this, then it is understood that the transistor will be in off condition. So when the transistor is in off condition, you can observe here VCE is equal to VCC. So what is VCE? Collector to emitter will be equal to VCC. So what is the voltage here? It is 10 volts. Next, since VCE, you may ask yourself how it is equal to 10 volts, because what is VCE here? It is 10 volts. So VCE is equal to VCC is equal to 10 volts. Since VCE is negligible, or we can assume to be 0, then IC is equal to VCC divided by RC. What is VCC? It is 10 volts. What is RC? What is RC here? It is 1 kilo. So 1 kilo. So 10 by 1 kilo. Kilo, if it transfer to above, it becomes milli. So it is 10 milliamp. Next comes to IB. When it comes to IB, it is nothing but IC divided by beta times DC that we have seen. So what is IC here? We need is 10 milliamps. What is beta DC? Beta DC, they are given it as 200. So 100 milliamps by 200 will give you 50 microamperes. So that is the minimum current required for the transistor to be in on condition. See, this is the value of IB necessary to drive the transistor to the point of saturation, that means in on condition. Any further increase in IB will ensure the transistor remain in saturation region. But this cannot be any further increased in IC. This is the minimum required current for the transistor to be in switch down. So A and B is done. Next, when the transistor is in on condition, VB is equal to 0.7. 0.7, we all know that a transistor is built by using diodes. You can see the combination of diodes. Here is the combination of N, P and transistor. So NPN transistor, if it is a 0.7 means it's a silicon. 0.7. So the voltage across RB is, what is the voltage across here? We need to find out. So what is RB here? RB is equal to V in minus VB. What is V in here? V in, what is the input voltage here? 5 volts. 5 volts minus, there is a drop at base to emitter. There is a drop. What is it? Drop. The drop is 0.7 volt. So that 0.7 volts, if you remove, the voltage is 4.3. So what is 4.3? 4.3 is the voltage of your V in. Okay. Calculate the maximum value of RB needed to allow a minimum IB of 50 microns. By using Ohm's law, we can follow the equations. RB is equal to, R is nothing but, R is equal to V by I. What is Ohm's law says? V is equal to I into R. So then what is R? R is equal to V divided by I. So V of RB, the voltage across here RB. So what is the voltage here? What is RB here? Nothing but your input voltage, V in minus VB. So it is 4.3 divided by current flowing through it. What is IB current flowing through it? It is 50 microampere. So 50 microampere is equal to, if you solve this, you will be getting 86 kilo ohm. So RB is equal to 86 kilo ohm. So this is how you are going to solve for the transistor to be in saturation region or on condition. Hope you understand. Okay, next simple topic, a simple application of a transistor as a switch. You will see here the transistor in circuit below here, if you observe, used a switch to turn the LED on and off. I am using this transistor to work as a switch. It should work as a switch. Either it should be in on condition or it should be off condition for my LED to be in on and off. So what I am doing here is I am generating some square wave for the input voltage with a period of 2 seconds is applied to the RB. Now the square wave is at 0 volt. First, what is the input here? The input is at 0 volt. Now what happens to the transistor when the input is 0? Transistor will be in off condition, or we can call it as cutoff region. Since there is no current, what is that? Collector current. The LED does not emit light because the condition between these 2 points are in off condition. The switch is in off condition. If the switch is in off condition, the current cannot flow from higher potential to lower potential through the load. So through the load. Now when the square wave goes to its high level, What is the condition here? When it goes to high level, the transistor saturates. That means there is an input to the transistor. The transistor is in on condition. When the transistor is in on condition, transistor works as a switch. So the switch is in on condition. The switch is in on condition means the forward bias, the LED and the resulting collector current through the LED causes it to emit light. So that means the load is nothing but your LED. It will be in on condition. Thus the LED is on for 1 second and off for 1 second. So it's a 50% duty cycle. So on for 1 second, off for 1 second. On for 1 second, off for 1 second. So it is a 50% duty cycle application. So you can use a transistor for switching on, switching off a particular device by supplying a power wave signal. Let us see a problem. An LED requires 30 milliamps to emit a sufficient light. Therefore, collector current should be approximately 30 milliamp. So what is happening here? We have a transistor here. A LED is connected to the collector, and this is the emitter, and this is base. So for the LED to be an on condition, minimum current required is 30 milliamps. You should see to it that the collector current will be equal to 30 milliamps, so that the LED will be in on condition. To make this as an on condition, or we can call it a saturation region, here use the double the minimum value of the base current as a safety margin to ensure saturation. It should be more than 0.7 volt. How 0.7 volt here? As we studied it, it's an NPN transistor. Transistors are built by using diodes. Here if I say it is a silicon diode, then the silicon diode to be in saturation region, it needs minimum of 0.7 volt. So that is the reason we are taking it 0.7 volt here. Okay, now given, what are the given? VCC is equal to 9 volt. It is nothing but the voltage here. It is 9 volt. VC saturation equal to 0.3. There is a drop here. RC is equal to 220 ohms. That is the resistor of your collector, which is here. Then RB is equal to 3.3 kilo ohms, which comes here. RB. Base resistor. Then we have beta DC, which is 50, provided by the manufacturer. Then we have VLED. VLED is equal to voltage of LED. LED needs minimum of 1.6 volt. Now let us solve this. What is IC? IC is equal to, what is IC? IC is nothing but the current flowing through the collector. So VCC minus VLED minus VCE. What is VCC? It is 9 volt. What is the voltage of LED to be in on condition? 1.6 volts. What is VCE? Collector to emitter saturation voltage? It is 0.3. So 9 minus 1.6 minus 0.3 divided by the current flowing through the resistor. That is nothing but 220 ohms. That comes around 32.3 milliamps. So this is nothing but your Ohm's law. I is equal to V by R. So here V is nothing but VCC minus VLED minus V collector to emitter saturation voltage. So I is equal to V by R, Ohm's law. Next, IB, minimum current required to make the transistor in a saturation region. IB is equal to IC divided by beta times DC. What is IC? IC we have found out 32.3 milliamps. And what is beta DC? Beta DC is given. It is 50. Now, IB is equal to 646 microampere. This is the minimum current required for the transistor to be in on condition. To ensure saturation, what they say, use the double the minimum value of the base current. See here. So what we are going to do now here is, what is IB? IB is 646 microampere. Now we are going to doubling it, which is nothing but 1.929 milliamps. Again, by using Ohm's law, IB is equal to V, voltage of your base VRB, divided by the current flowing through the resistor. That is nothing but RB. So what is VRB here? We can see in the diagram here. I am just sending a input voltage here. So input voltage is nothing but VRB is equal to voltage across for this is nothing but V in minus the voltage across V base to emitter. So what is base to emitter voltage? It's nothing but 0.7. What is the V in voltage here? That's what we are going to find out. But we know what is RB. What is RB here? RB is nothing but 3.3 kilo ohm. Now cross multiply this. V in minus 0.7 volt is equal to 2 times of IB. 2 times of IB is nothing but 1.29 milliamps. 1.29 milliamps into RB. RB is 3.3 kilo ohm. Now if you solve this, the V in voltage will be 4.96 volt. So what should be the input voltage? So V in should be 4.96 volt for a minimum IB current of 1.29 milliamp. That's what we have solved here. Okay, next. Coming to the next topic, oscillators. Okay, next is oscillator. So what is an oscillator? Oscillator is a circuit that produces a periodic waveform on its output with only the DC supply voltage as an input. If you consider an oscillator with an DC supply with some components which produces a periodic waveform like this, a periodic waveform. That's a simple way of telling what is an oscillator. So what is an oscillator? An oscillator is a circuit that produces a periodic waveform on its output with only the DC supply voltage as an input. So repetitive input signal is not required here. If you observe here, we are not giving any signal here. We are not giving any input varying signal here. We are just giving an input DC supply to it, and it is generating a signal, that is a periodic waveform or synchronized oscillations. In some applications can also be used. The output voltage can be either sinusoidal or non-sinusoidal depending upon types of oscillators. Here what I am showing is a sinusoidal oscillations, but it cannot be, it is not said that it is always a sinusoidal. It can be of non-sinusoidal depending upon type of oscillators we are going to use. So here if you see, there are two major classifications of our oscillators. They are called as feedback oscillators and relaxation oscillators. So when I say our feedback oscillators, there is a feedback to it, that we will see we'll be studying in the coming slides how this feedback oscillators will work, and as well as relaxation oscillators. Okay, that is about your classification of oscillators and oscillators. So what is the principles of oscillators? So here in the principles of oscillator, the operation of an oscillator is based on the principle of positive feedback, where portion of the output depends in the feedback of the input without phase change. So always remember, the operation of an oscillator is based on the principle of positive feedback, where portion of the output signal is feedback input with the without any phase change. I'll come back to that. What is that? You may not understand if I say that. See, there is a output. What it says, there is a positive feedback. I'm giving a positive feedback to this. A portion of your output will become an input to your oscillator. So this is without phase change. That's what the principles of oscillator will work. The portion of oscillator is based on the principles of positive feedback, where portion of the output signal is feed back into the input without phase change. So we are not changing the phase. So that without phase change are fed back to the input. So that is called principles of oscillator. Okay. Next, here some of the mathematical values for a loop gain. So for a loop gain, I have given a name it as T. So what is T here? Gain into, that is the gain of the amplifier, into VB is equal to 1. It should be always equal to 1. This should be equal to always unity, where AV is the voltage gain of the amplifier. And what is beta? Beta is nothing but VF, frequency, VF divided by V out, is the feedback portion of the output. There is nothing but the feedback portion of the output voltage. See, if AV is equal to 10, then the feedback portion of beta should be 1/10, 1 divided by 10. So these principles of oscillations are illustrated below. As you can see here, the transfer function of the circuit shall be A of F is equal to gain divided by 1 by AV. That's not what gain into beta times. So this is the transfer function. This is the transfer function of the oscillator. Okay. So there are some conditions you need to understand for the oscillators to work properly. So we'll see that conditions. What are the conditions? So if you observe here, first one, the phase shift around the feedback loop must be effectively equal. So I note written here, the phase shift around the feedback loop must be effectively equal. The second one, the voltage gain around the closed loop feedback loop, that is nothing but loop gain, must be equal. That's what we have seen in the previous slide. It should be equal to 1. It should be equal to 1. That is the condition. Okay. Next, the voltage gain around the closed feedback loop is a product of amplifier gain and attenuation of the feedback circuit. What it says, the voltage gain around the closed feedback loop. So you can see here, there is a closed feedback loop. A part of the output is given as a feedback to the input of the circuit. It's a positive feedback. It's the product of amplifier gain and the attenuation of the feedback circuit. Okay, next, if a sinusoidal wave is the desired output, if I am thinking about a sinusoidal wave as in desired output, a loop gain greater than 1 will rapidly causes the output to saturate at both peaks of the waveform. If you observe here, it should be equal to 1. If it is greater than 1, then it will causes the output to saturate at both the peaks of the waveform. Then your output will be distorted. You will not get the proper output. To avoid this, what we do is, some of the form of gain control must be used to keep the loop gain at exactly 1 once the oscillator has started. That's what we are going to do here. Here B, what it does, it is nothing but a gain control. So this gain control will take care such a way that your gain should not be greater than 1. So it should be equal to 1. So if it is a gain is equal to 1 means then you will be having a stable oscillation. That's how the two conditions has to be met by the oscillators. So one is the phase shift around the feedback must be equal to equal. The gain, voltage gain around the closed loop must be equal to 1. That's nothing but the unity. So this is about the two conditions of your oscillations or oscillators. Next, so here we will see RC phase shift oscillator. So here there are three types of feedback oscillators. There are three types of feedback oscillators that use RC. There's nothing but R and C is nothing but resistor and capacitor combination circuits. Why we use this? To produce a sinusoidal output. And where we use this? We use in Wien bridge oscillators, phase shift oscillators and twin T oscillators. We'll be studying these things. Okay. So where we use this feedback oscillators that use RC circuits, one is Wien bridge oscillator, phase shift oscillator and twin T oscillator. Okay. Generally RC feedback oscillators are used for frequencies are up to 1 megahertz. This you have to remember, it's very important. Where we use this RC feedback oscillators, they are used up to a frequency of 1 megahertz. The Wien bridge is by far the most widely used type of RC feedback oscillators for the range of frequencies. So most of your Wien bridge, most means the Wien bridge uses the RC feedback oscillator for the range of frequencies. Here some of the circuits, if you can observe here. One is an amplifier, it's an amplifier, and or else we can call it as op-amp, operational amplifier, we call it as operational amplifier. Op-amp means operational amplifier. The input here given is to the negative, so negative feedback. So the positive one is grounded. So it's a negative feedback because there is a 180-degree phase shift. Phase shift. There is a 180-degree phase shift. So because there is a 180-degree phase shift, then the output is given to the negative. So we need a positive changeover. So here we are using three capacitors: capacitor 1, capacitor 2 and capacitor 3, and three more resistors, R1, R2 and R3. All are of same. C1, C2, C3 are same, R1, R2, R3 are same. So for the first tank circuit, which we call it as a tank circuit, here R and C combinations. You can see C with R, there is a 60-degree phase shift for your output. And one more tank circuit, we have 60 plus 60, it's a 120 phase shift. I need a 180 shift, which is your output. Again one more, which gives you 180-degree phase shift. So this is your RC phase shift oscillator. Very simple technique, will be used in most of the oscillators like phase shift oscillators, Wien bridge oscillators, twin T oscillators. Let us see the output, how exactly it works. Okay. Here if you observe, how many capacitors we are using here, C1, C2 and C3, all are same. And here R1, R2, R3, all are same. 100 kV I am using, here 100 picofarad we are going to use. Okay. So the input voltage here is 6 volts. I'll show you this. I'll show the output how it works. So let me see first what is the input here. Input is 6 volts, 100 kilohertz, and this is the waveform. Let me explain this. So just changing the settings here. So that is nothing but your amplitude variations of channel B. and the channel C. We are taking 4 channels. We're taking 4 channels. So here you can see here there are 4. One is yellow color, which is denoted by yellow color. So one more is blue color, one is red color, and one is green color. So yellow color is nothing but the input, and we have 3 outputs, which are nothing but your 60 degrees, 60 plus 60 plus 60 plus 60 plus 60. That is nothing but 180-degree phase shift. So blue color, red color. There is a phase shift in red color compared to your yellow color, and there is no change in your green color. See, if you observe here, there is no phase change. And let us see the blue color. So there is a slight change, that is 60-degree change, 60-60, and one more, that is your 180-degree. So there is a 180-degree phase shift. So if you observe here, there are 4 signals. One is input, one is your output. Okay. So that is how your system works. Hope you are understood with this. Okay, we will see in the next class, the next topic. Thank you.